right? We're just using the physically motivated numbers for supernova feedback and so on, and star formation. So one thing we can do instead is we can try to calibrate our stellar feedback so that we empirically fall back into these relationships for the stellar mass versus the halo mass, right? And that's what many simulations like FIRE or NIHAO and so on do for their physics. But of course, the whole problem doesn't end there, right? Because once we actually match the stellar mass versus halo mass relation, there is so many other physics so many other properties that we need to get right. So for example, methane enrichment, we will want to get the shapes of our galaxies right, rotation curves, so on. And typically it is the case that we don't get all of these right at the same time. So then the question for our simulations is, what are we missing, right? What could we include in our simulations to get these things right? And there are three components that we know, well, these physics are well known, and we know they are important for galaxy formation in multiple ways. And the most convenient thing is that we can actually simulate them, right? So if we include this in our simulations, we might be helping ourselves to get more realistic galaxies. So we know they are important. Stellar radiation in particular, Sam really nicely showed that one of the main things that you do when you include radiation in your simulations is you pre-process the gas around stellar particles so that the supernova explosions, when they go off, they become more efficient. Hartley also showed that they can also affect the actual evolution of the galaxies themselves. Magnetic fields might not be that important for the global properties of galaxies unless you go something very extreme with primordial fields. But we do know they play a role on these smaller scales by affecting magnetohydrodynamical turbulence, the mixing of different modes, and so on. And then in particular, and very importantly, they actually play a fairly important role in star formation, right? When you go to the smallest scales, magnetic fields and the local magnetic field kind of regulate how efficient star formation is and how rapidly it proceeds. And one of the nice things that we have in Ramses through Julian's star formation is that we can account for this in the same manner, or trying to mimic the way that this happens in nature, also accounting for the role of magnetic fields. And finally, cosmic rays, they're back on vogue again. They finally come back because they help us a lot get the realistic outflows that we observe in galaxies around us. And so the whole argument here is that they provide us with this non-thermal pressure that generates a smooth gradient, right? So gas can be continuously pushed out of galaxies without having to be extremely heated. And also, as Kurra will show later on, they might also affect the supernova remnants under the position of momentum. So what I'm going to be doing is I'm going to be throwing all these physics into the same simulations of a dwarf galaxy formation. Of course, this is done with Ramses. When we go to this general configuration, just very broadly, MHD is going to magnetic fields are either going to be seeded through a primordial field or injection with supernova explosions. These values are aiming to give us magnetic fields in the galaxy that are on the order of several microgauss, so we match observations. And then when I probe these primordial fields, I would argue that they are particularly strong, maybe, even though they are quite below the current observational limits, maybe galaxy formation simulations might be able to rule these models in the future. So in that regard, I would regard my injection of magnetic fields to give us a more realistic scenario than these primordial fields. When we go to the radiative transfer, I'm doing something very similar to Sphinx, so I'm kind of following Joki here. And when it comes down to cosmic rays, this includes diffusion and streaming, and the coefficient for the diffusion that I'm using is something in the middle of the road of what most simulations use, and tends to be in agreement with most observations, like spallation of high energy particles in our Milky Way and so on. But basically, I'm trying to be very agnostic and just choose conservative physics to see what the result is in the formation of our galaxies. Going down to star formation, once again, I'm using this magnetothermoturbulent Julian's prescription. And so the idea here is that you only form stars when you beat the local support of the gas through gravity. And of course, we also account for the local properties of the gas, meaning not only the turbulence, but magnetic fields and thermal properties. We form stellar particles with this, and then these stellar particles are able to, typically, as we would want them to, generate feedback using Taysom's mechanical model. They not only provide us with density, momentum, and energy, and metallicity, and all this stuff, but they also can provide us with, as I said before, magnetic fields and cosmic rays. So when I inject magnetic fields in supernova explosions, I'm using 1% of the energy of the supernova in the magnetic energy. This is a fairly small percentage, but it gives us these about 10 to the minus 5 Gauss magnetic fields on 20 parsec scales, which is a good match to the typical energy density that you would get in supernova remnants. And cosmic rays are exclusively sourced through supernova explosions, as it is typical in most simulations these days. And I'm choosing this 10% number, which is within the 20% typical acceleration of supernova remnants of cosmic rays, and is quite, I would say, fiducial in that sense. Finally, radiation, we have 3 energy bins, but everything is ionizing for hydrogen, hydrogen 1, helium 1, and helium 2, again, very Sphinx-like. And so finally, getting into the simulation, here you can see the box on the left. It's a fairly big box for a fairly small dwarf, but we do get a box that doesn't collapse in itself, and we do have a very high resolution in the zoom region that goes down to 7 parsecs. And as you can see here, our stellar mass is also fairly small, so that we get to resolve most of the dynamics and the different explosions. And indeed, this is a fairly small stellar particle mass, but we're still treating every particle as a single stellar population. So all of this comes in, and then our galaxy comes out, right? And as you can already see, I have a lot of different models, and different models, depending on the physics they include, they look fairly different. Just to give you a bit of a view of how the galaxy looks like in mock observations, here we can see our full physics RT-CR MHD model in optical, in near infrared like JWST-like, and then radio synchrotron as SKA would observe it. So I have a lot of simulations, but I'm going to try to simplify the picture a bit today by grouping them in different groups of increasing complexity going downwards. So there's these 4 models with no feedback. Then we actually include the standard feedback with star formation and standard feedback and stellar feedback in supernovae. Then magnetic fields on top of that. Then I'm going to include radiation, and some of these radiation runs are just radiation and standard feedback, and some of them also merge with magnetic fields. And finally, we go to the most complex run where we have cosmic rays, magnetic fields, that's always there. And then in some cases, we include radiative transfer. So again, as I said, you can see increasing complexity from blue, red, purple, then orange, and then green. So with all of this, the question is, can we actually produce realistic galaxies or actually match a bit what we observe around us in galaxies? So just to put us into context, the typical stellar mass versus halo mass relationship looks like this, particularly if I'm, instead of using the stellar mass, I'm using the baryon conversion efficiency, which is just the fraction of baryons that it's going into stars. And we can compare, for example, with the Beruzzi et al. 2013 relations, right? Of course, our dwarf galaxies tend to be much lower mass. In particular, I'm going to be focusing on these range here. So the game we have to play is that we have to get this Beruzzi stuff and extrapolate to lower halo masses. So if I zoom in into this bit of the graph, we see now a bit of a smaller interval of halo masses and also lower values. And given that I'm studying the same galaxy at different snapshots in time, one thing we can do is we can plot the same halo at different redshifts, and we'll just get different masses. So if I do that for no feedback, what you're going to see is that the galaxy evolves, initially forming a burst of stars, and then it just runs away, forming stars with no regulation whatsoever, and we end up converting pretty much most of our baryons, even 100%, close to 100% of our baryons into stars. Of course, that was expected, and then the other thing that we expect is that if we include stellar feedback, what happens is this gets regulated, our galaxy starts to get the lower amount of star formation going on, and then our stellar mass is supposed to not go so crazy over time. So this ninja star, as Deborah usually calls it, is this typical, the fiducial supernova feedback that everybody pretty much uses with realistic numbers for the energy and so on. And you can see that the galaxy falls fairly close to the Beruzzi et al. 2013 extrapolation at redshift of about 0, right? So what I've done here is I run a few of my simulations further in time just to see what happens, because I'm not going to be able to run all the models down to redshift 0. The other thing I want to mention here is that we also have this boosted feedback model at the bottom. This is very Sphinx-like. It's a factor of about 4 compared with the standard physics. And you can see that it very nicely matches or falls close to Beruzzi at redshift 6, but at least for this particular galaxy, it kind of overshoots in suppressing star formation by lower redshift, right? So we kind of would want to get the best of both worlds, I would argue. We can add magnetic fields. I'm going to ask you to ignore the strong primordial fields here because they just do their own thing and it's going to be hard to explain in this very little time. But if we just look to the other 2 models, what typically happens is that we form a burst of stars early on. This burst is larger than in the no magnetic fields case because we get some additional support and that grows our giant molecular clouds. But once they collapse, they form stars, and this basically almost quenches our galaxies. And there's not much significant evolution, and it just falls back on the same place as the standard feedback did. We can add radiation. I guess I'm 3 minutes away from finishing, Sham. If we add radiation.
Yeah, sorry,
okay.
Just about.
If I add radiation, what happens is that we actually see that early on we can suppress some star formation. This is because once you form your stellar particles, you can already stop the process of star formation by evaporating the giant molecular clouds. However, these galaxies, they will do all my runs with radiation, actually, they will have a much higher gas content. So these gases are going to be able to form stars, and for this particular orange line that you see in here, you go back again to the same track by redshift of about 3 or 4. When we include magnetic fields, what happens is that now we form these more massive clouds of gas, as I mentioned before. But now these more massive clouds, and we are not fully sure about this particular aspect, I need to look at it in more detail. But our presumption here is that the more massive stars are able to further suppress the initial star formation, and you actually fall very close back to this boosted feedback. What does really happen is that effectively you eject all the gas from the galaxy and you quench the galaxy down to redshift of about 6 when the gas falls back into your galaxy, and then we just jump again to the previous track, right? So this is just a tale of going back to the origin. This is strong primordial field run is doing a different thing. I can go into details if you're interested, but I just want to move into cosmic rays. So when we have cosmic rays and radiation, we're actually even more efficient now in expelling the gas from the galaxy, and the gas is even being pushed further away from the galaxy, so it doesn't fall back by redshift 6. Then again, at redshift 5, we have a merger with a companion, and now we actually get all the gas into our galaxy, back into our galaxy, and we form stars. So once again, we are getting close to our same result. And of course, we don't get to redshift 0, but I would argue that it is quite plausible that the evolution is going to be similar to what happened with the standard feedback, and we're going to be on top of Beruzzi 2013. The other interesting thing to mention here is that if we compare with observations of local dwarf galaxies, these are from Justin Reed, where he estimates the mass of the halo. These simulations with cosmic rays and the boosted feedback as well are the only ones that provide us a closer match to the lower halo masses to what the observations are giving us. And then at higher masses, or at lower redshifts for us, our galaxies go back to what the local group is doing. So that's kind of encouraging in that line. Whereas again, the boosted feedback seemed to mask this early on, but then it overshoots a lower redshift. I have a lot of results for you, but I don't really have too much time. So I'm just gonna maybe quickly mention something again. So I mentioned on the gas content of this system. So these are the size mass relationships for galaxies. If we focus on the gas on the left, this is the size of the gas. Sorry, the label is a bit cut. Perhaps the most interesting thing is, as I mentioned before, yeah, okay, I'll just mention this and finish. The no feedback is doing its own thing. Then when we include feedback, magnetic fields and non-magnetic fields reduce the gas content. But when we include radiation into these galaxies, we get a factor of about 2 or a bit more gas content into our galaxy. So that's quite encouraging. I don't have time to talk about outflows. And maybe just very briefly, when we look at metal enrichment, these are local group observations, and cosmic rays match it quite nicely, whereas boosted feedback don't. So long story short, supernova alone don't give us galaxies that really match observations, but RTC-RMHD seems to be driving us in the right direction. So even though this is expensive, we might be getting there, including more physics. This will be done soon, so keep an eye on the archive if you're interested. Thank you.
Awesome. Thanks very much, Sergio. Cool. We already have questions. So I guess I'm going to take Arturo first in order of, I think, seniority without knowing people.
So is it me first?
Yeah, go ahead.
Okay, so very interesting work. Thank you. I guess with such a high resolution in dark matter, have you looked at the halos? Do we have a core in this dwarf?
Interesting. Yes. We do get more core profiles with cosmic rays, but of course, so the whole thing. Right. Sorry, I'm going out of the presentation here. But when we look at the density of the inner bit compared with the mass of the halo, we do see that our cosmic ray simulations seem to be falling a bit lower. Particularly, it seems actually I would argue radiation seems to be doing most of the work for us. This is redshift 3.5. So we are not really coarse yet, but I reckon if Justin was here, he would say that you need multiple cycles to get there. So maybe if we go to Redshift 0, this would be the case.
So do them to Redshift 0.
I don't know. It seems to help so far, down to about 1.7 years.
No, really interesting. Thank you.
Cheers.
Cool, thanks. Harley next.
Hi, Sergio. Really nice talk. It seemed like you based one of your conclusions quite strongly on where the galaxies fell on the stellar mass halo mass relation, but at redshift 3. Yeah. And I was wondering if you thought that that was actually a fair metric, because do we actually think that galaxies won't have a higher stellar mass conversion efficiency at higher redshift compared to low Z?
Sure. Yeah, no, you're very right. So I wish I had more time to elaborate, but the whole premise here is that we evolve a subset of simulations to redshift close to 0. And we don't see much growth in the halo. You can see already here is about, I think it goes on to 6, 7. Yeah, it grows a bit, the halo, but we don't see much star formation going on. The galaxy seems quenched. So in principle, we would just expect the galaxy to move parallel to this black line if, again, this no evolution holds. I would also say that the Beruzzi 2013 extrapolation is not necessarily something you have to match, because you have updated muster and so on. But I wouldn't say exact. So in that line, I wouldn't really put too much weight on the matching the local the Beruzzi relationships, right, or these theoretical relationships. I would look a bit more at the local dwarf measurements. So the points I'm plotting from Justin here, and of course there is the caveat on how you get the halo masses from observation, which is a very complicated process as well.
Awesome. One more question from Oscar, and then we'll move on to the next talk.
Okay, yeah. So you basically answered my question there, but just to add in about the muster relation, right? I think the only if you were to trust the muster relation, you would actually it would be the boosted feedback model that would match.
Yeah, you're very right.
So, but I understand this is you're looking at the systematic changes with feedback. So you have to do something. Yeah.
Indeed. So just to be, sorry, because all of this doesn't transpire in the talk, right? But just to be very open with everybody. I'm only showing this Beruzzi relationship because if I include muster, it is actually below my graph. So it would make my scale look a bit too compressed, but muster would fall, the extrapolation would fall around here, right?
I just don't know.
So I'm sorry, that probably was a bit, maybe it looked like I was saying, we are matching this and therefore we're happy. I wouldn't make a strong conclusion out of that, because these theoretical relationships at these low masses are a bit more hand-wavy.
Awesome. Johan, I'm going to suggest you ask this in the Slack. So yeah, people go ahead and check the Slack, and we're going to get Corentin now talking about cosmic rays in the ISM.
Okay, thank you, everybody.
Yeah, thanks, Sergio.
Okay, can you see the slides fine?
Awesome. Yeah, perfect.
Okay.
Go ahead.
Okay, perfect. All right, so good afternoon, everyone. My name is Rodriguez, and I'm a PhD student at the Department of Astrophysics in Oxford. Today, in this last day of our meeting, I'd like to show you some of the results of what began as my master's project, but has become soon to be published paper. I'm talking on behalf of these people over here. I'll talk about the interesting new possibilities that cosmic ray physics provide to galaxy formation, particularly centered on the importance of cosmic rays to supernovae. The outline of this talk is as follows. Firstly, I'll give a short introduction to the problem of feedback. It's something that we've covered quite a lot, so I'll try to make it brief. Then the choice of a numerical setup will be explained before diving into some of the major results we have obtained, including mock observations and implementing a subgrid model in cosmological simulations. Also, I'll present the ongoing next step that this line of research has motivated, and the conclusion that we can extract for interest for the topic of cosmic star formation. I guess we've talked quite a lot about this, but within the lambda CDM paradigm, one of the subjects of most interest has been the clear mismatch between the halo mass function and the galaxy mass function. The clear lack of star formation efficiency in the low and high mass regimes has been suggested to be due to the effect of supernova feedback and AGM feedback. Focusing on stellar feedback, early naive implementation of supernova feedback in numerical simulations suffered from overcooling and due to limited resolution, and failed to provide the deposition of energy required to get the difference in variance content of the galaxy and star formation history. Since then, grid models have been used to accurately measure this and follow the evolution of supernovae, by relying on artificial boosting of the supernovae energy, like in the Sphinx, where they use a factor of 4. This is usually claimed to be originated in missing physics like magnetic field, radiation, and cosmic rays, which is the topic of this talk. So nowadays, there are many theoretical and observational studies that argue in favor of cosmic rays as a fundamental galactic component. And why that's the case? The arguments behind that are that cosmic rays possess very unique physical properties. The bulk of the energy resides in the gigaelectron volt protons, which behave as a relativistic fluid with a soft adiabatic index. And their charged nature allows them to diffuse strongly along their field lines. In summary, they suffer less cooling and they can travel larger distances without losing energy. Therefore, in the past about 10 years, many works in the literature have studied the implementation in models and simulations. However, since cosmic rays need an accurate modeling of magnetic fields, this has been only possible until quite recently. The results from different groups are in agreement. Cosmic rays help increase the mass loading of winds, making them colder and denser, and improving the metallic enrichment of the CGM. But what about the effect of cosmic rays to its source? How cosmic rays affect supernovae remnants? That's something that has been out of reach and unexplored for quite long. It's the topic of this talk. As I've mentioned, the numerical implementation of cosmic ray physics in magnetodynamical simulations can now be used to extract useful predictions with respect to the effect of cosmic rays. We use the Ramses MHD version with the constraint transport method to achieve a divergence free up to numerical precision. We also make use of AMR, so we reach 0.4 parsec resolution, and gas is allowed to cool. Cosmic rays have been implemented thanks to Johan Dubois and Benoit Comesson, which includes anisotropic diffusion, streaming heating, and hadronic losses. We inject cosmic rays in the central A cells of the box, in the same place we also put the thermal energy of the supernovae, and we fix the diffusion coefficients across the entire domain, and also all simulations. The box has a uniform density, and we explore two magnetic field configurations, an aligned uniform field, and then a turbulent using following a Kazantsev spectrum. Thank you to Sergio Martin-Alvarez. If you'd like to hear more about these initial conditions, just contact me later, Sergio. So now I'll show you a first look at these supernovae. There's nothing too much interesting about the hydro runs in the top. Then you have MHD, and then you have cosmic rays here. You can see that for at least for the time that we evolved these simulations, we confirm the results of previous works that a magnetic field, a uniform magnetic field, doesn't make much of a difference to the supernova remnant. However, for the case of the cosmic ray run, we clearly see differences. The bubble becomes slightly cylindrical. But I think that what you may have noticed is the peculiar conical structures that can be seen in the pulse. Since cosmic ray transport is fundamentally guided by the magnetic field lines, these are escaping the supernova remnant through the magnetic pulse. That escape of cosmic rays are driving really strong outflows, which destroy the shock around that region. How does it affect the evolution of the supernova? Well, in this figure, which is of great interest, you can see the time evolution of the outward radial momentum of the full supernova remnant. We compare a set of simulations here, but you can see that the two main phases are the focus of our simulation setting. Firstly, the initial growth of momentum during the set of Taylor phase, and then the plateauing of the momentum during the snowplow phase. We see that the MHD runs in purple here follow the hydro run consistently with previous work. However, we find something truly fascinating for the cosmic ray runs, which are over here. They appear to follow closely the known cosmic ray run in the set of Taylor phase, but once they reach the shell formation time, which is the point where cosmic ray energy begins to dominate the energy budget of the bubble, you see a new phase in the evolution of the supernova remnant, something completely new, marked by an exponential growth of momentum, which is stronger for a higher cosmic ray fraction. So you can see here 0.1, 0.05, and 0.01. So the previous plot helped us portray this new cosmic ray dominated phase that you want to see how that consistently changes with cosmic ray energies and densities, we provide here an updated version to the Naban-Ostriker paper, review paper. In here, you can see that the change in momentum with respect to the locus, which is given by the gray dots here, circles here from previous work, increases as time goes on. So you can no longer measure the momentum just at 1 megayear as it's been usually done. By looking at the red arrows, it's clear that the cosmic ray runs move away from the locus in the P versus N plane towards higher momentum, with a difference increasing with time. Additionally, you can see two main trends. Higher cosmic rays, which are given by the outline in darker greens, have higher increase of momentum, and then the increase of momentum becomes higher for lower densities. Additionally, we don't see any trends with magnetic fields. Now we move on to have a look at how the initial conditions of the fields actually affect the simulation. And in here you can see slices through the centers of these runs in the MHD and the cosmic ray cases. As these magnetic initial conditions do not come with consistent density initial conditions, they drive perturbations in the ambient medium, which can be seen by these patches. The expanding shock, now much more isotropic, resembling the results of the hydro runs, encounter these patches, and which survive the shock compression, as they can clearly be seen inside the bubble. With a constant turbulent spectrum, we can expect that the diffusion coefficient is isotropic, with a value a third of the maximum parallel to the field lines. The result is an effective isotropic cosmic ray diffusion, which allows for two main things. Cosmic rays stay for longer inside the bubble, allowing higher cosmic ray pressure at later times. And secondly, the majority of the pressure exerted is not really in just one single direction, as we saw with the outflows in the aligned cases, but rather we have this a spherical pressure gradient of cosmic rays pushing the ambient gas farther. As we can see here, when we compare the solid lines with the lower opacity, which are the aligned runs from before, the tangled runs have a higher momentum at the same time, as far as can be able to evolve them. We've also looked at how these supernovas look in Mach synchrotron observations, so we can see if they have some kind of signatures that observers could look at. For that, we've used the RT code Polaris, which relies on the spectral number density distribution of cosmic ray electrons in the simulation. However, there's a little problem because the cosmic ray implementation in Ramses neither follows the evolution of the cosmic ray proton spectrum nor the distribution of cosmic ray electrons. In order to avoid these difficulties in translating between protons and electrons, we use the simple cosmic ray 2 model from Reisel et al. 2019, in which we assume that the cosmic ray electron distribution comes from the equipartition with magnetic fields. The resulting 1.4 gigahertz maps can be seen here. Show the results for our fiducial run. From left to right, you can see the MHD run, and then all the ones with cosmic rays with increasing cosmic rays. Firstly, as you know that for the watchful ones in the audience, that yes, the total luminosity slightly decreases with higher cosmic rays, and also with the brightness of the rims. It's not a super clear effect, but it's there. We argue that this is due to lower magnetic amplification due to the increased pressure behind the shock coming from cosmic rays. But the main interest of this plot is the clear resemblance of our emission structure and the polarization structure of our runs with all the supernova remnants like the Tycho and SNR. Similar for the aligned runs, the simulations using the tangled ICs also show the dominant emission coming from the post-shock regions, although nothing compared with the amount of intensity that we saw before. Now we have like a decrease of about 2 orders of magnitude, so that's a big change. And we don't have that uniform emission from the outside of the bubble. It's interesting to note that despite the turbulent nature of the magnetic field, we still have the radial structure of the polarization vectors. So that's quite an interesting thing compared to what people say in observations. And on the other hand, these ones are capable of approaching the really low polarization fraction, and also that polarization fraction decreases behind the cosmic rays. So this supports the theoretical claim and observational claim that a high contribution of the tubular magnetic field in supernova remnants. So this will be included in a soon to be published paper. So check your archive quite soon. we've extended the lens from this project to see how we can implement this in cosmological simulations, which is probably the interest of many of the people here. Considering the trends that we have in between ambient density and cosmic ray diffraction, it is possible to build a simple model that accounts for these effects in the effects of cosmic rays. We started by using a really simple fitting power law, in which we depend on density and cosmic rays. And the idea behind this is that we increase the energy, the initial energy of a hydro supernova evolution in order to reach the momentum at the end of the cosmic ray runs, but in the hydro runs. So therefore, this simple model in which the initial energy of the supernova remnant is boosted can be introduced in your favorite semi-analytic model or numerical model, really, really straightforward. So we have precisely tried that. The next simulation is a high-resolution cosmological simulation, in which the initial conditions, we have performed 3 different simulations. Okay. A standard hydro run, in which we include an uncalibrated mechanical feedback, so we can model, a cosmic ray run with cosmic ray energy injected at 10% of the supernova event, and then a standard hydro in which we use our model. Before anything else, I should say that these slides follow a part of a project that is still in its earlier stages. Nevertheless, I'd like to show you some preliminary results, so you're quite excited for the next time we meet. So in this projection, you can see phase views of the night galaxy in the cosmic ray run compared with the hydro run at roughly the same time. There are many morphological differences that we can talk about, but the main thing that is really interesting is the strong decrease in the stellar mass or in the cosmic ray run compared to hydro and MHD. It's a decrease of 1 text. In fact, cosmic rays appear to sustain a very low star formation efficiency. The galaxy appears to be gas dominated at all times compared to the hydro and MHD. This can be related to how cosmic rays allow gas to cool in the ISM with a collapsing, similar result to what Ricarda Beckman showed for her clusters on Monday. But well, let's go back to the comparison of a simple model to this cosmic ray simulation. Cosmic ray here is in green, the orange is our model, and then the blue is the regular hydro with a subgrid mechanical feedback. The hydro run with the subgrid model consistently reduces the stellar mass by a factor of 2, but nevertheless, it's not accurate to the cosmic rays. You still need to include a proper on-the-fly treatment of cosmic ray feedback. So what are the main conclusions of this type project? Well, firstly, for supernova remnants, we need to understand that cosmic rays definitely make a difference in the evolution. An alignment in green, when they have an aligned magnetic field in initial conditions, they drive really strong outflow, which is something that hasn't been seen before. And cosmic ray at some point later in the evolution of super remnants, they feel a new phase of evolution. This momentum boosting can reach a factor of 4 to 6 times higher than hydro counterparts. So you can now argue for your boosting of 4 in your simulations. Then when we look at how the initial condition of the magnetic fields affect the evolution, definitely a tangled ICs can change how the momentum of the cosmic rays is imparted to the ambient medium. And then we've done some mock observations, and we're saying that aligned runs are able to reach the luminosity of observations, but the tangled ones support the idea that a really high degrees of turbulent magnetic fields is in supernova remnants. We've included this in a model. However, our model, while really simple, is only able to decrease the stellar mass by a factor of half, which still falls short or compared to the 1 text decrease by including cosmic rays. And which means that the take-home message for all of you guys is just to remember that cosmic rays can definitely affect the evolution of supernova remnants, but you can parameterize that effect also. But if you want the full effect of cosmic rays, you need simulation. So a little bit of a happy, sad feeling about all this. So I hope you guys got everything, and thank you.
Yeah, perfect. Thanks very much, Carl. All right, any questions? All right, if people are not putting up their hands for a second, they're thinking about questions, I'm going to ask. So would you expect a similar effect with wind bubbles? So you have this figure where in the set-off phase where it's not really cooling efficiently, then you have, not so much effect from cosmic rays, but when it cools efficiently, then the cosmic rays help accelerate it. I mean, would you expect a similar thing if you have like an evolved wind bubble, which is starting to cool down, but,
Yeah, definitely. Yeah, probably. I mean, that's something that we'll try to have a look at in the zooming simulations to see if some wind-driven bubbles actually experience some kind of acceleration when the thermal energy decreases quite a lot, because cosmic ray energy remains there for a while.
Right.
It will depend because of the diffusion that we use, because something that I haven't really pointed out too much is that the diffusion coefficient that I use in the supernova simulations is much lower. Well, it's one order of magnitude lower compared to the cosmological run. So that's something that could make a difference in how cosmic rays are confined to our region and how can they provide that extra momentum.
Right. Okay, thanks. Any more questions? Otherwise, encourage people to go on the Slack and keep discussing.
Okay.
Leave it a little while anyway, because it's not quite time yet for the next talk. But I guess, Corentin, you can already start putting up your slide. Awesome. So yeah, go ahead and ask more questions on the Slack, and I'll give it up to Corentin, who's talking about the thing that's on the screen right now.
Yeah. Okay. Well, thank you. So today, I'm a postdoc researcher at University College London, working with Andrew Punt and Hirina Paris on the causal origin of angular momentum of properties of galaxies. And it's my presentation today is going to be quite orthogonal to the ones we had today, in the sense that I'm not tweaking at all the physics, but I'm trying to tweak the other free parameter. All right. So why is angular momentum important in the first place? Well, if you think about the morphology of galaxies, we know pretty well that with increasing mass, we have more and more elliptical galaxies, especially at a high mass end, and spiral galaxies tend to disappear with like merger, transforming spiral into more elliptical galaxies. We have had plenty of talks today discussing the subgrid physics, so the effect of AGN, supernova feedback, cosmic rays, or dust on the properties of galaxies. But one dimension that has not been explored at all is angular momentum. So imagine that you can have the same galaxy with the same physics and the same mass, and you change the angular momentum. Are you actually reproducing this morphological diversity? It is also quite important when you think about intrinsic alignment, because if you are able to predict the angular momentum, you can also predict the alignment of galaxies, which come as a nuisance parameter in weak lensing survey. So it means that if you want to understand the formation of galaxies and the onset of their morphology, you need angular momentum. And for upcoming cosmological weak lensing surveys, it's also a key ingredient. So our current understanding of angular momentum is in 4 steps. So at very large scales, angular momentum is being acquired by the gas and the dark matter through torque with the large scale structures. It is then transported towards the galaxy, where it is then torqued down when you get close to the inner halo. And then somehow magically it mixes in the disk and in the bulge, and it settles into a star, into a stellar disk. If you look at a volume rendering, this is from one of my simulation. If you look at the volume rendering, what is quite interesting is that this gas flows actually along cold streams, especially at high redshift and high mass, and funnels down the angular momentum acquired at large scale down to the center of the galaxy, where it then forms the galaxy itself and the disk. So what it means is that if you want to form a galaxy, a realistic galaxy, you need to capture the large scale structure, you need to capture properly this inflow towards the galaxy, and then you need to have like a proper description of what is happening in the center of the galaxy. Okay, so how do we do that? So if I rephrase what I just said in terms of requirements, if you want to study properly a galaxy, you need to resolve the scale heights. So I'm going to say that you need 30 parsec resolution or less. That's a bit I mean that's a bit arbitrary, but that's probably enough just to resolve the scale height of the galaxy. You need a cosmological setup because you want to be able to capture the large scale structure, hence the acquisition of angular momentum prior to being accreted onto the galaxy. And so for this, we have had today, yesterday, and the day before yesterday, many different approaches in terms of making numerical simulation. So either isolated simulation, which are great because you can push as much resolution as you want, but then you don't have at all the cosmological environments. Large cosmological simulations are great, but you don't have a really good handle, well, you don't have a really good resolution. And so the best way to study properly angular momentum acquisition for galaxies is through zoom simulations. But the issue is that with zoom simulations, you have, for the galaxy you're simulating, you have a fixed angular momentum accretion history, and you have a fixed cosmological environment. So you can't really disentangle the effects of the subgrid physics from the effects of either the accretion history or the environments. So what I want to present today is two methods to actually modify both the angular momentum and the cosmological environment using Ramses. All right. Yeah. So first thing, what is behind these three red dots, red question marks? So one way to do this is through genetic modification. So it's a method that has been developed by Andrew Ponzan and some of his students, including Martin Ray, who's probably in the talk. And so the idea is that you go back to the initial conditions and you can make targeted modifications to the region that are going to form a galaxy to affect its subsequent evolution in a resimulation. So for example, here, that is from the method paper by Stopliera last year. We have one simulation that yields this galaxy. That's a fake image, but we don't really care. And if you increase initially the initial density, you end up with a galaxy that is a bit more massive. So that's way of doing it. So if I go back to my initial diagram, it means that we have a way to change from the initial condition the mass. Now, how would you do the same with angular momentum? So this is a method that I developed. In the initial conditions, this is a bit too technical maybe, but imagine that you have a region which is going to form eventually a galaxy. You can compute the initial angular momentum using this formula here, which is essentially q minus q bar is just the position, and this term here just the velocity. So it's essentially angular momentum is equal to position cross velocity. The bottom line here is that if you have the density, you can derive the potential using the Poisson equation, and you can also derive the gradient of the potential, so the acceleration, which gives you the initial angular momentum. And if you can compute the initial angular momentum from the density field, you can also make the same kind of modifications that I just showed for the density field, but this time for the angular momentum, which means that you can crank up or scale down the initial angular momentum of a given region directly from the initial conditions. Which means that you can, if you change the density of a region, you change the mass of the halo that will form later in the simulation. And if you change this term here, you're actually changing the angular momentum without changing the mass of the objects. So that allows to explore this 2D parameter space and see how it affects the galaxy or the dark matter halo to start with. All right. Okay. So what I've done then, just to like the first step that I've done is use this method to generate initial conditions and then run dark matter only simulations with it with Ramses. This is with a very classical dark matter only setup, 256 cube. I modified 7 different halos and I changed their initial angular momentum with 8 different scenarios. So decreasing by a factor of 4 and up to increasing by a factor of 4 the initial angular momentum. And all of this leaves the mass of the halo fixed, which means that I'm really exploring the y-axis here along this diagram, except I'm working with halos, not galaxies. So I have the same halo, same environment, but different initial angular momentum. And if I draw the evolution of the angular momentum of the region that I just modified as a function of time, so x is a function of time, y is angular momentum. The red line is the original simulation. And then, for example, the blue line, the dark blue line, is what I obtain if I decrease initial angular momentum by a factor of 4. And the red line is what I obtain if I increase it by a factor of 4. So naively, what you expect is that if you multiply by, say, a factor of 2 in the initial conditions, you end up with something with an object that is rotating twice faster, and conversely, if you divide it by 2. In other words, if I have this reference simulation, I can predict the value of the red line or the value of the blue line from it. Okay, I'm just going to skip that. The interesting bit is that if I do this prediction, so I use the reference simulations to predict the value that I expect in the one with the modified angular momentum, I can compare that to the tidal torque theory, which is the reference in terms of predicting the angular momentum. And I get results that are much more accurate. So I get results that are, this is on the right side here, I'm showing the scatter of the prediction with respect to the true value. So the smaller the number, the more accurate the prediction is as a function of redshift. And the colored lines here are what I obtain if I modify the initial angular momentum using the technique, and I use the reference simulation to make a prediction compared to tidal torque theory, which is the state-of-the-art theory. And I get an improvement between a factor of 2 and factor of 3 in terms of the quality of the prediction. So what it means is that if I change the initial angular momentum, I change the subsequent angular momentum of the object that is going to form out of it. So it's a practical solution to change the angular momentum of objects in simulations. Okay, I'm going to skip that. The interesting bit is that now you can do, instead of just doing this with the dark matter, you can also do it with the baryons. So this is ongoing, some ongoing results. So it's not finished at all yet. So I'm running cosmological hydrodynamical simulation zoom-ins, 30 parsec resolution with star formation, agent feedback, Ramses, the New Horizon model from Johan Dubois, and the tracer particles, which allow me to find the baryons in the galaxy and then trace them back to the initial conditions. By the way, they're included in Ramses, so if you want to use them, well, feel free. And the idea is that because the baryons fall deeper in the gravitational potential, they are going to, well, if you make modifications in the initial conditions, it's not going to affect which baryon end up in the galaxy or not, which means that they should be easier to control than the dark matter. And indeed, if I do it, and I measure, for example, the angular momentum of the galaxy, so I just find the galaxy, compute its angular momentum as a function of time, I get these 3 lines. So gray line is the reference simulation. The red line is what I obtain if I increase the initial angular momentum by 20%, and blue line is what I obtain if I decrease it by 20%. And I target a modification at redshift 2, and indeed, by doing this, I end up with either an increase or a decrease of the angular momentum. So it means that I have a practical solution to change the future angular momentum of a galaxy. So I can spin it up or spin it down. And then, of course, well, now I want to see what effect it has on the galaxy, and I can't tell you because it's ongoing. But stay tuned, and I should have the results relatively soon. And I should say again that this is very, very preliminary, so you should take it with like a massive bowl of salt. But the angular momentum of the galactic baryons seems to be controllable and predictable from the initial conditions. And so I can modify it and explore the angular momentum dimension of the formation of a galaxy. Okay, and before leaving, I also wanted to present a second thing. So I just showed how you can modify the angular momentum accretion history of a galaxy. Now, what about changing the cosmological environment surrounding a galaxy? And so here, the idea is that imagine that you have the same galaxy as before. So once again, it's just a fake image that I screenshotted from one of Johan's paper. Imagine that you have this galaxy forming here. The question is, what would this galaxy resemble if instead of forming here, it had formed, let's say, here next to a cluster, or what if it had formed instead in a void? So the idea is to, I developed a method called the spacing technique, where you essentially take, in the initial conditions again, you draw the boundary of some region, and you take the blue field here, which is your reference field, and you insert it in another field here, the red one, and so that allows you to study the same galaxy, but in different environments. And if you then feed that into Ramses and you integrate with time, you obtain in the blue region here, you get something that is relatively similar, and outside of it, you've got a totally different environment. Okay, let me skip. So I used this technique, the spacing technique, which is detailed in my paper, again with the same dark matter only simulation, and I cut and paste the initial conditions of some dark matter halos, and I see how it affects their properties. And just to start with, I just looked at the concentration. The first thing that I see is that by doing this, the halo that I obtain in my resimulation, so the spliced halo, where I change entirely the environment, well, the halo that I obtain have roughly the same mass, plus or minus 20%. So I obtain the same halo, which means that it's a practical solution to take a halo and insert it wherever you want. And it also allows to show that, for example, by doing that, you're able to reproduce half the scatter of the concentration of the entire population. If you want to know more about that, well, you can ask me questions. Okay, so it means that there is a solution to modify the cosmological environment of a galaxy or a halo. I haven't done yet with a galaxy, but that's work in progress. And so I'm going to jump to the conclusion. So I presented two methods. First is genetic modification of the angular momentum, which allowed me to show that the angular momentum is predictable. You can also apply the same method to baryons, and I'm currently looking into what happens, whether the galaxy is able to self-regulate its spin. Can I trigger spin flips? Can I form blue nuggets? Is there a link between angular momentum accretion and supermassive black hole growth? And I also propose a second method, the splicing methods, which allows to embed the same halo in different environments. So you can take a galaxy or a halo, insert it next to a cluster, next to a filament, whatever. And I intend to use it to study filament quenching or the link between the cosmic web and galactic spins. Yeah, and well, I mean, the cherry on the cake is that everything is readily usable in genetic, and everything is plugged in with Ramses. So if you are interested in the methods, well, feel free to contact me and use it. Thank you.
Awesome. Thanks very much, Corentin. And we already have a question, so go ahead, Martin.
Yeah, thank you. I actually have two questions, but I'll start with one. The first one is on the splicing when you say about the concentration, because a lot of the concentration scatter is thought to arise from like merger history, accretion history, formation time, and so on. So when you say it's the same halo, have you looked at whether the accretion history over time are the same on top of the final mass?
So, I mean, given the time I had to do the presentation, I didn't go in too much into the detail. When I say same halo, I mean that's half the particles in the resimulated halo were also in the original halo. So they have to share more than 50% of their particle, and the mass has to be within plus or minus a factor of 2. But of course, the accretion history is different, and the angular momentum history is probably also different. So I don't put constraint at all on that. Which means that when I say that I reproduce half the scatter of the concentration, that also includes the fact that some halo will form earlier or later, which is also known to correlate with a concentration being smaller or higher, respectively.
Okay, cool. Thanks.
Cool. Did you have another question, Martin?
Yeah, I had another question on the prediction of the angular momentum from the initial condition. Mm-hmm. So you got this plot with the red, blue, and gray lines at redshift 2.
Yep.
Yes, this exact plot. And so there's this huge jumps in the plots.
Sorry, are you talking about what I'm highlighting right now?
Yeah, the bottom plot.
Yep. Yeah.
And this huge jump seems to make quite a big difference. What are those? Are those like specific merger time or something like that?
So the three jumps here are actually the same merger, and so what is happening is that by changing the angular momentum in the initial conditions, what you're actually controlling is the impact parameters of stuff falling in, and it also changes the time at which it falls in. At least from my first analysis. So it seems that when you decrease the angular momentum at redshift, targeted at redshift 2, what you're actually doing is that you're making a merger happen slightly earlier in the history of the galaxy. And when you increase it, you're actually doing the opposite. You're getting stuff shots at the galaxy slightly later in the history of the formation of the galaxy. So this is what we're seeing here, but that's only for one galaxy. I have 40 more to be analyzed, so I'll be able to give a more definite answer in like a year or so.
Awesome, thank you.
Cool. We still have a little time for questions, so if people want to ask, then go ahead. It's a bit unusual that workshops are actually this far ahead, so Good work, everyone. Otherwise, we can always queue up the next talk and take it to Slack if people have any questions that they think of at the last minute. But yeah, feel free to keep asking questions for another minute or so.
Meanwhile, I'm going to advertise a bit the new features in YT.
Yeah, please do. Go ahead. You have a minute, so.
Okay, yeah. Just like since the last time I talked at the Ramses meeting, there's been many new features in YT, mostly that I pushed myself for Ramses. So you can now select subdomains in YT to read only a small part of your simulation. The reader has been optimized quite substantially. You can compute gradients directly on the grid. You can project particles on the grid and interpolate the grid at particle position. And it now supports radiative transfer, MHD, sinks, gravity, well, all of the things that I tried. And you can make volume rendering, isosurfaces, raycasting, stuff like that. So if you're interested, feel free to ping me.
Cool. All right, I'm going to take one very quick question from Christoph, and then we'll switch over to Florent's talk.
Hello, can you hear me?
Yep.
Okay, so I just want to come back to your introduction where you mentioned that your talk was a bit offset with respect to the others who were focusing on, I guess, changing the internal physics rather than environment. So what's your take-home message about the relative importance of doing one or the other?
Well, I think that if we want to reach any definite conclusion, we need to do both at the same time. One is not enough. If you only tweak the physics, then you're always going to end up with a result, which is that changing the physics is super important. But it happens that if I change the formation history of a galaxy, I end up with the same simulation, with the same result. So it means that's really the two things are like the formation of a galaxy is a balance between the accretion and whatever happens within the galaxy. So you need to weigh the importance of the two at the same time to be able to reach any conclusive results, especially with zoom simulations where you only have one object. You can't disentangle the effect of this specific object having a specific formation from the effects that the baryonic physics has. So I would say that I have to do two at the same time, unfortunately.
Okay, thank you.
All right, thanks, Corentin. So I guess we should move on now to Florent. You can share your slides.
All right, thank you. Thank you very much, Sam, and the organizer for this very cool meeting, and for the opportunity to talk about the history of the Milky Way told by its mergers, which is a project done in collaboration with Oscar Gertz here in Lund and our nice Wintergatan team. Some people are actually listening now. Eric Anderson and Martin, also Martin Ray, are in the audience. So Wintergatan is what you see in the background. It's a cosmological zoom-in simulation of a Milky Way-like galaxy reaching 20 parsec resolution. And one of the initial motivation that Oscar had to start this very nice project was to disentangle the different stellar populations in the Milky Ways and try to connect that back to what the observers tell us. And one of their favorite plots to tell apart different stellar population is to go to a chemistry plane. Here on the x-axis, you have the Fe over h, the metallicity, and on the y-axis, you typically have the abundance ratio between alpha elements and Fe elements. And long story short, after billions of such plots, what appears is that you have basically two big populations. This one up there in the high alpha over Fe sequence is tracing the thick disk of the Milky Way, which is chemically hot. So high velocity dispersion, high orbital eccentricities also, and made of stars older than 10 billion years, more or less. And in addition to that, you also have a different second population, which is down there in what we call the low alpha over Phi sequence, which is mostly corresponding to the thin disk made of kinetically colder stars and much younger. You also have a bit of mess in between the two here. These stars are mostly found in the halo, and somehow they connect to a thin disk, but it's not fully understood yet how this works. So in this plot and all the other versions with different elements that you can think of, you have a lot of information encoding the past history of the Milky Way, how it assembled, which were the physical conditions in which stars were born. And it's very difficult to decode and to go back to history to understand the formation of the Milky Way, in particular, and the galaxies in general. So I think everybody in this audience will agree that one very cool tool to do that is to use simulations. Unfortunately, they haven't reached a consensus on the topic. If you look here, for example, at fire simulation or eagle simulation, they would not find bimodalities in their chemical plots, as we see in observations. And if they find one, they are very, very rare, which leads us to conclude that the Milky Way has a very specific path of galaxy formation. However, with cosmological zoom-in simulations, so a suite of simulations, with Auriga, we could find a bimodality, which can be explained by two discrete episodes of gas accretion. So basically, you form your Milky Way in two GOES, quite separated, so each of them having their separate chemical signature. But the picture gets even more complicated when people not using cosmological context found that they can actually find bimodality. So with no cosmological context, no accretion, no mergers. And they explain that by a transition between the high redshift, turbulence, clumpy galaxy star formation, quite violent, very efficient star formation, into the more quiet regime that we have in the present day at low redshift. And this would trace a change in the enrichment of the galaxy and therefore this bimodality here. So clearly no consensus from the simulation part. But all these simulations have one problem in common, is that they don't use the best code in the world. So this is why we came up with Oscar Agertz to Wintergatan using Ramses, obviously. I spare you the technical details, but once more, we have a cosmological zoom-in simulation of a Milky Way-like galaxy. So you see here the creation of a gas in blue. The last major merger is coming in. You have a lot of minor mergers also. And the last major merger is doing its magic. And you see a quite complicated picture in the surrounding of the Milky Way, but also inside the disk of the Milky Way, a lot of things are going on. So using this simulation, we are being able to look at the chemical properties and actually retrace the origin of stars when they form and with which chemical composition. And indeed, we did find a bimodality in Wintergatan. As you can see here, you can clearly have the high alpha sequence followed by the formation of the low alpha sequence happening right now. So just a disclaimer, in Wintergatan, alpha is traced by oxygen only. And of course, and like I would say any simulations, we suffer from uncertainties on the chemical yields, on the solar abundances that you need to normalize them, on the binary fraction, on the type 1a supernova weights, all these things which, if you want to describe that from first principle, you basically need stellar radius resolution and much more detailed physics, collisional dynamics, and even stellar interiors, if you want to do that properly. So we are far away from that, and we still have to rely on calibrated subgrade recipes to assess something like that, which is probably at least part of the reason why we don't have a perfect match with observations. In terms of methodicity, we're kind of okay, but when it comes to ratio between abundances like alpha over Fe, we are clearly too high in this simulation compared to the observations, something that 0.2, 0.3 dex too high. It's probably because of this reason. So no quantitative match, but quite a good qualitative match in terms of, first of all, the presence of bimodality and the shape of the features that we have in this plot. And therefore, we can use this simulation to try to understand what's going on and what could be this. And we see that this chemical bimodality arrives at redshift about 1, shortly after the epoch of the last major merger, which is quite interesting because a lot of things happen in the last major merger. One of these things being the trigger of a starburst. And starbursts in general are a period of short depletion time. So I remind you, it's the ratio between the mass of gas divided by star formation rate. And if you have a short depletion time, this means that you have a short time scale for star formation. So yes, it's cool by itself, but it's even cooler if you compare that to other time scale in your simulation or in your galaxies, like the time scale for chemical enrichment, in particular in Fe. So in that case, during a starburst, it could be that you form stars faster than you chemically enriched in Fe. So what does it mean? This means that you increase your alpha. This is coming from the type 2 supernovae, so the core collapse supernovae, while Fe is not the supernova type 1a, they are not kicked in yet, so Fe remains constant. So in other words, the starburst will temporarily boost your alpha over Phi ratio. So now if we compare that to what we find in simulation, this is a map of that. Every little dot represents one star forming event. Not all of them are plotted for clarity. And the color is coding the log of the depletion time. So let me walk you through that. We start, of course, at low metallicity, so to the left. And what happened here is that the galaxy is not experiencing starburst yet. It might be a bit counterintuitive, but if you want to understand why, I will refer you to Alvaro's talk right after the break, and he will tell you all about this mystery. Later, the Milky Way is in place at more or less 34. It forms a disk, and it will respond to the interaction and the mergers by triggering starbursts. And you see these little spikes in purple point here, which are short depletion times of mergers, which show this boost of alpha over Phi, temporarily, of course, and then it goes back down. And after the last major merger, well, by definition, you don't have many more major mergers left. So you don't have anything to trigger a galactic-wide starburst. So you just have a much quieter environment everywhere, and you can reach this low alpha over Phi sequence. So to summarize, at the end of the merger phase, we don't have any more tidal excitation, so you don't have high turbulence maintained by the interactions, so no more starburst, no more boosted alpha over Phi, and therefore you're allowed to go down to the low alpha over Phi sequence and to build your bimodality. But turns out at the same time, more or less the same epoch, you also have an intrinsic evolution of the galaxy itself. By burning its gas and forming stars, you decrease the gas fraction. And if you do that, you're going to change the stability regime. We're not going into the details about that, but I refer you to our latest with Alessandro Romeo and Oscar Agertz on this topic. Long story short, if you lower your gas fraction, this means that the relative weight of stars and gas in your stability criteria is going to change. And basically, you go from a clumpy instability, so massive clumps, into something which looks better like spiral arms. So end of the clumpy phase, formation of spiral arms, smaller giant molecular clouds, and different chemical enrichment, different regime of star formation, less turbulence, colder disk, less excitations, etc. And then you can also go down to the low alpha over Phi sequence. So in the end, all this is a combination of both external and internal factor in the Milky Way. So to summarize all that, in the age metallicity diagram, this is a track that we have put together representing the bulk of the galaxy. And one interesting feature is this little thing there when we ignite a formation channel, something like 9 billion years ago. And this is not unique to Wintergatan, this has been seen in other simulations too. So to try to understand what's going on, let me gather some clues. We find it at lower metallicities in the bulk of the galaxy at the epoch of the last merger, but it's not made of accreted stars. It's stars formed in the Milky Way and not in satellites. And it connects to the rest of the disk later at later age, so on the left there. So to understand what's going on, we need to take a step back and look around the galaxy at this epoch. And here what we are seeing is in this map of the gas density, you see the Milky Way here. It's surrounded by an outer disk, which is not perfectly aligned with the Milky Way itself. It's tilted because it's fueled by a cold flow filament there. And in addition to that, you also have the last major merger there, but be careful, it's just a projection effect. It's not part of the same cosmological filament, as you can see if I rotate the camera around. So you see different structures, different alignments, different geometry, and therefore different kinematics, but also different metallicities. Now I'm going to color code by metallicity. You see low metallicity in yellow, so these vertical filaments, which is fueling the outer disk of the Milky Way. But the Milky Way and the last major merger appear in dark blues, much higher metallicities, and the filaments connecting the two is kind of intermediate metallicities in turquoise. So if I summarize all that, what we have is the Milky Way right there, the last major merger here. The filaments connecting the two has been polluted by two massive galaxies, the Milky Way and the last major merger, and therefore their outflows has increased the metallicity in these intergalactic filaments. So it's a bit higher than the minimum, I would say. And the Milky Way sits at an intersection with another filament appearing here in yellow, which has a much lower metallicity because it's not polluted by two galaxies, only by the Milky Way. And therefore, what happened there is that this filament is fueling the outer disk of Milky Way with low metallicity and also low density medium. So what we need to do now is to trigger star formation in this outer disk. And this is just going to be done by the last merger, which will do its job, which is merging. And just like in any interacting galaxies, in an interacting system, the overlap of the two gravitational potentials of galaxies will create big volumes of compressive tides. So instead of stretching the matter, you compress it. This is what you see in these red areas here. And by compressing the matter, by compressing the gas, you can, right, thank you. You can actually reach high enough density to form stars. And this is how just the passage of last merger will trigger the formation of stars in this low density and low metallicity outer disk. So with time, the outer disk and the inner disk will line together because of gravitational torques. This is done in a couple of billion years, and they will form a big extended disk galaxy. So you might think this is a particularly fine-tuned scenario, but if you think of it, it actually requires two cosmological filaments to fuel the Milky Way, which is quite common for a galaxy of this mass. And then the major merger will do the rest. It will just trigger the formation of stars at the time it's needed. And it actually has been seen after we published that people have checked in their large volume cosmological simulation. I think this one is from TNG, when they found it quite commonly in the Milky Way mass range of galaxies. So it could actually be a generic process, a generic feature of galaxy formation for massive disks. So this is a summary in terms of the growth of the Milky Way, in terms of half mass radius of the gas. You see here mock images of the simulation, and they all have the same scale. So you see how you go from something relatively messy and small into something which is much more extended and structured with spiral arms at the end after the last merger when the galaxy is growing in the quiet phase. So basically what we came up with is this evolutionary track when this material is coming from the inner galaxy and the accreted material, in addition to this track coming from the outer disk, tilted first and then aligning with the rest and connecting with the bulk of the galaxy. In the metallicity alpha over phi plot, this is what it looks like. You have the high alpha over phi component made from inner and accreted matter. Most of the low alpha phi is also coming from there, but this low metallicity end is coming from the outer disk. And exactly at the time when we are coming up with this analysis of the simulation, observers came up with their analysis of spectroscopic data. I think this one is Apogee with machine learning. Spare you the technical detail again, but basically you can compare what we say at the top with their evolutionary tracks in blue and red at the bottom. They say at least qualitatively the same story. So I think I'm running out of time now, so I will jump to conclusion, and I will leave you with this summary slide, which is basically the full formation scenario for the Milky Way in Wittgenstein. And if you are hungry for more details, I will give you the menu for the 3-course meal that we put together, and I wish you a bon appetit.
Awesome. Thanks very much, Florent. That's an excellent talk. All right. Who has questions? Yeah, go ahead.
Hi. So great talk. Thank you. I cannot avoid thinking about the satellite disk when I see all of these stories of the outer disk coming back to alignment with the main disk. Have you looked at the satellite disk or something like this? Is it too soon to look at it? I don't know.
Yeah, a student is actually looking at that right now. So the result will come in the next month.
Can wait. But can you tell us, is it there? Is it not there?
It's too early to tell.
All right. Fair enough. Thank you.
Cool. Thanks, Amandine.
Hi. Thanks, Florent, for the really nice talk. I have a question. Are you able to answer the question about the state of the disk of the Milky Way? There is this controversy of whether there are two disks, old thick one and the new thin one, or whether it's a continuum. That's been ongoing for 10 years now.
Yeah, that's what one of the main things we looked at with Oscar Agertz And basically what we found is that there is more like a continuous evolution between the two disks. There are clearly two separations, but there is no sharp transition between the two in basically any parameter space that you look at. Would it be geometrically, kinematics, chemistry?
So it's not bimodal, in short.
It is bimodal, but not with the gap in between. If you
yeah, no, not bimodal with a sharp cut. That's what I mean. Yeah. It's continuum. Yeah, okay. Because I think on the observational side, people still disagree.
Yeah, it's not totally clear. Yes, I think if you want my 2 cents on that, I think the difference could come with different formation history or different timing of the history of the Milky Way. For example, if you have a early late major merger, that could be a bit different. You can maybe stop forming stars for a while, or you can quench if you reach high mass enough, this kind of thing. So this is maybe what we have to play with to get such a diversity of answers.
Yeah, and also I think the early observations sometimes had systematics that are probably now resolved with Gaia. For instance, you had stars that were older than the edge of the universe.
Yeah. And it's quite limited to the solar neighborhood too. So you
yes.
don't probe the entire, yes.
All right, I'm going to take one more very quick question from Johan and then hand over to the organizers for the break.
Thank you, Florent, for the talk. You mentioned the alphas, the alpha elements were a bit underabundant. Can you elaborate a bit on this?
Yeah, it's actually the ratio of alpha divided by Fe, which is a bit. It's actually too high in the simulation. So Fe is kind of okay, but I think it's really when you go into the ratio of abundances that you get into trouble, because both species have to be quite precise if you want the ratio to be in the ballpark of the observations.
Okay, but what is typically the difference of observation? It's 0.1 dx, 0.3 dx?
In Vitergatan, yes.
Yeah.
Yeah.
So what is
0.2, 0.3. In other models that varies quite a lot. You have I don't think it's a single offset. It's more like a skewed distribution. It's not fully understood why. So probably a combination of lack of constraint on, or lack of very precise model of type 1a supernovae, and also chemical mixing and all these things.
All right, I suggest we move any other discussion to the Slack, because it's now gone time. So any more comments, Pierre, before we head off to the break?
Yeah, so thanks everyone. I just put the WonderMe link in the chat again, if you want to use that to gather for coffee and discuss further. Before you leave, I'm going to ask the next speakers to try their presentation.